Hello everyone, I am Xiaoying Wang. In this talk, Weiyuan and I will present our scalable data science track paper, ConnectorX, accelerating data loading from databases to data frames. This is a joint work between Simon Fraser University, Columbia University, and Tencent. Data scientists nowadays are using data frames to interact with the data. However, data, especially in industry, are stored in databases. In order to bridge this gap, existing tools like Pandas provides this with SQL function, which could fetch the data from a database to a data frame. However, existing libraries are notoriously inefficient in this task on large datasets. In particular, we load the TPC H-line item table with a scale factor 10 from a database running on one AWS EC2 machine to another instance. And we found this procedure could take more than 12 minutes and requires 95 gigabytes of memory, while the data itself is only 7 gigabytes in the CSV format. This inefficiency could make the data loading a bottleneck in the machine learning pipeline. Here we use the most popular pandas with SQL, for example. We construct an end-to-end machine learning pipeline according to a prior paper on the real-world dataset it proposed, which consists of nearly 13 million DDoS traffic flows. The pipeline consists of three main steps: data loading, pre-processing, and model training. When we break down the time of this pipeline, surprisingly, we found the model training and pre-processing only take 14 and 2 minutes correspondingly, while the data loading using with SQL takes more than 19 minutes, which is more than half of the total pipeline running time. This indicates the importance and potential gain of speeding up this procedure. This inefficiency has plagued the data science community for a long time, and users care about this issue. We found a bunch of users posting questions complaining it and cannot find a good solution on websites like Stack Overflow. This is why we decided to build ConnectorX to tackle this issue. And we have successfully helped many users boost the performance of this data loading procedure in various tasks. ConnectorX is a client library. It aims to bridge the gap between database and data science by improving the existing SQL function with only a single line of code. It achieves efficient data loading for large datasets in terms of both time and memory usage. More specifically, by only switching from Pandas to ConnectorX using 4 CPU cores, we speed up the previous TPCH example by nearly 13 times, from 12 minutes to within 1 minute, and with 3 times less memory footprint. Before introducing how we achieved this, we need to first know how WithSQL works so that we can identify its bottlenecks and opportunities. Here, we still use the most popular pandas WithSQL, for example. Internally, when we invoke WithSQL from the client side, the SQL query will be executed inside the database, and its corresponding results will be transferred back to the client in the format of raw binaries through network. The client library will first deserialize the binaries into intermediate objects using an existing client driver, and then converts the objects into the final data frame. Knowing how WithSQL works, let's first see why it is slow. We break down the time of fetching the TPC H-line item table and show the result of Postgres and MySQL in this figure. Here, we use the orange color to represent the procedures that happen on the client side. Surprisingly, we found that instead of the server or the network, the client-side processing is actually the bottleneck in our test, which takes more than 80% of the total time for both databases. This gives us the opportunity to speed up WithSQL by only optimizing the client-side implementation. Next, we try to figure out why is WithSQL memory costly. We inspect the memory footprints of the same example. We found the raw binaries returned by Postgres is around 12 gigabytes, and the size of the final pandas data frame is around 24 gigabytes. However, we observe that the peak memory usage of this WithSQL is more than 95 gigabytes, which is almost 4 times larger than the final result. We identified 2 reasons that cause this issue. First, the intermediate Python objects are extremely memory inefficient and can inflate the dataset into more than 50 gigabytes. Second, all these 3 data copies are kept in memory until the final data frame is generated. This unnecessary duplication is another reason that caused the high memory consumption. After answering these 2 questions, next, Weiyuan will introduce how we tackle these issues in ConnectorX.
To understand how ConnectorX improves Pandas ReadSQL, let's first take a look at how Pandas ReadSQL downloads data. Let's assume that we are going to download data from the student table. So we first issue the query to the database, and then the database execute the query, produce a query result. And then database will serialize the query result into a binary string, and the binary string is transferred to the local machine and received by Pandas. After that, Pandas will serialize the byte string into Python objects and wait for the whole query result to be complete and deserialize all of them into the Python objects. And these Python objects are stored in the main memory. After receiving the whole query result, these Python objects is returned to a pandas data frame by pandas. And after all the Python objects are written, pandas will destruct these Python objects to free up memory. As we see that in this process, step 2 to step 4 are actually happened on the local machine. So we want to improve these parts. From the analysis Xiaoying mentioned in the previous slides, we know that the size of the query result that is represented in the wire protocol or in the binary string is actually 4 times less than the size in Python objects. This is due to the Python object overhead. So the first thing ConnectorX do is replace the Python object with compact representation of the query result. This greatly reduces the memory consumption of this data loading process. We also observe that if you use single thread to download data, it is very likely that your CPU will be the bottleneck. The reason is that deserialization is a very CPU consuming task, and if you use single thread, then you are less likely to saturate your network. So instead of using a single thread in ConnectorX, we use a parallelism. So when taking a query, ConnectorX will first rewrite the query into multiple subqueries. We call this partition. And then for each partition, ConnectorX will spawn a separate worker which works on a specific CPU core, and the worker is responsible for download data from the database for that specific subquery. The worker will then write data to a specific partition in the data frame, and then for all the workers, they take over different CPU cores, thus achieve parallelism. In ConnectorX, we also use stream processing instead of batch processing, which is used by pandas read-SQL. In pandas, it will not write the final data frame until the full query result is received and deserialized into the main memory, which essentially doubles the memory consumption. Here in ConnectorX, it will try to deserialize the binary string, which comes from the network, as soon as possible, and then write the deserialized value to the corresponding pandas data frame as soon as possible. This greatly reduces the memory footprint. In summary, ConnectorX is built upon these key ideas. In order to save memory, we use an efficient data representation for the intermediaries so that we can avoid Python object overhead. We also use stream processing so that we can reduce the memory size of the intermediate results. In terms of speed up, we use parallel execution that make us to leverage multiple CPU cores. We also have pre-allocation and Python string allocation optimization, which are not talked about in this talk, but they are described in our paper. So please refer to our paper. In addition to speed and memory usage optimization, as a practical object, we also want our library to be easily extensible. So we use a modularized architecture, which means that if you want to add a database, then you can just add a source driver, which located on the left-hand side of this chart. Also, if you want to add a data frame, then you can add a destination driver, which located at the right-hand side of this chart. So in either case, you don't need to touch the center part, which is responsible for parallel data transferring. There is also another problem called type mapping when you do data transferring. Basically, different systems can have different logical types, and even with the same logical type, they can have different physical representation. For example, if you have a GPA column, which is represented by decimal in Postgres, and when you download it, it becomes a float 64 in pandas. The question is, how can we let ConnectorX know that how to convert the decimal into a float? If you do it manually for each types, then it will easily become a very trivial and hard to maintain task. So what ConnectorX do is by inventing a new domain-specific language, which is based on macro. And when you write this domain-specific language to express the type mapping, our macro engine will expand the macro into executable codes at compile time. This greatly reduces the code size of ConnectorX by 97%. Next, we are going to talk about our evaluation result on our performance and memory usage optimization. So we benchmark our library on TBC Edge dataset, which contains 16 million rows and 16 columns. Our baselines include pandas, Dask, Modin, and TurboODBC. All these four have some way to download data from the database to corresponding data frames. We did our experiment on AWS EC2 R5 4x large, which contains 16 CPUs and 128 gigabytes of memory, and the network bandwidth is 10 gigabits per second. We have two machines. One machine deploys our database, and another machine we treat it as a local machine that is responsible for running the read SQL. First, it's speed comparison. So we compared our library with all other different baselines, and we can see that ConnectorX is much faster than all other baselines in all scenarios. We also have a memory comparison, which shows that ConnectorX has 3x less memory footprint on the client-server DBs and 2x less on SQLite. We also want to report the impact of ConnectorX as an open source project. It currently has 730 GitHub stars, 475,000 PyPy downloads. It currently supports 6 different database protocols and 5 different data frames. It has multiple use cases, including loading data for machine learning model and ETL and ELT. We have also integrated with other projects like Polars, data prep, and modding. Before we jump into the conclusion, I want to talk about the big picture and where ConnectorX is in this big picture. So in order to make data science faster, we have main 2 directions. One is move compute to data, which allows you to write code in the database, and also move data to compute, which allows you to do faster data transferring from database to computation nodes. For example, there's new data format, and there's new database supporting data transferring, and also there's new systems that is specifically for client-side data downloading, and ConnectorX is one of them. Okay, so in conclusion, read SQL is a common first step in data science pipelines, but existing solutions are slow and memory costly. The reason they are slow and memory costly is because not enough optimizations in the read SQL functions on the client side. And our library ConnectorX is an efficient read SQL without modifying existing database servers, which provides you up to 10x speed up with 3x less memory usage compared to pandas. Thanks for listening. If you are interested in our library, please take a look at our repo and don't hesitate to give us a star. And if you are interested, you can take a look at our technical report besides our paper. Thank you.